Hi viewers, welcome back to our channel Raveendra for Students. In today's video, we are going to see about Gauss law and its applications. Before going to start our video, if anybody watching our channel first time, please subscribe to our channel and click on bell icon also to get the notifications when I upload any new video. Gauss law was first discovered by the German scientist Carl Friedrich Gauss in the year 1835. So actually what is the statement of the Gauss law we will see. So if you see the statement, it is states that the net electric flux density through any closed surface is same as the total charge enclosed by that surface. That is, mathematically we can write the statement as closed integral over S d bar dot ds bar is same as the total charge enclosed, that is Q ENCL. So here in the Gauss law we have to remember three keywords: net electric flux density, closed surface and total charge. Then with the help of these three keywords, the Gauss law is the net outward flux through any closed surface is same as the total charge enclosed. So that can be remembered by this mathematical equation: closed integral over S d bar dot ds bar is same as the total charge enclosed by that closed surface. Remember, here it is closed surface. That's very important. All the problems solved by using Coulomb's law can be very easily solved by applying Gauss law, but there are four conditions to apply Gauss law. So what are the four conditions to be satisfied to apply Gauss law? We will see now one by one. First one is the symmetry should exist for the charge distribution to apply the Gauss law. Then second one is, once the symmetry exists, identify the closed surface called the Gaussian surface for that existing symmetry. And then the next condition is the tangential component of d bar on any point on that Gaussian surface is 0. And the last condition is the normal component of the electric flux density d bar on any point on that closed Gaussian surface can be found by equating it to the total charge enclosed. Already we know Gauss law. What is Gauss law? Closed integral over S d bar dot ds bar is same as Q enclosed. Q enclosed is nothing but the total charge enclosed by that closed surface called a Gaussian surface. That closed surface here was called as Gaussian surface. So already we know that the electric flux density will be always in the normal direction. So first we have to select a closed surface called as Gaussian surface. So to that Gaussian surface on any point we have to find out the d bar. So on that particular point, if it is tangential, the value is 0. If it is normal, then we have to equate according to Gauss law, that is same as total charge enclosed. So like that, by satisfying these conditions, we can solve any electrostatic problem very easily. Gauss law can be applied to any electrostatic problem if there exists a symmetry for the given charge distribution. But there are 5 major applications to apply Gauss law. Now we will see those 5. The first one is point charge. Second one is infinite line charge. Third one, infinite surface charge, infinite volume charge, and then uniformly charged sphere. So to these 5 major applications, we are going to use Gauss law, how to find the electric flux density due to all these very easily. And students, already we know how all these 5 different cases, how the electric field was obtained by using Coulomb's law. There we have done, we have evaluated the complex integrals. Now here, by using a Gauss law, without evaluating the integral, we can get the electric flux density directly. We will see how to get those here. The very first application of our Gauss law is point charge. So how to apply Gauss law to find out the electric flux density due to a point charge? So for that, let us consider a well-known coordinate system, that is Cartesian coordinate system, which consists of 3 axes x, y and z as shown. Now So in this Cartesian coordinate system, let us assume that there is a point charge at the origin of this coordinate system. A q was placed like this. Then, in order to apply Gauss law, we need a symmetry for this point charge q. So what will be the symmetry for this point charge q? So for that symmetry, we have to construct a surface called a Gaussian surface. So onto that Gaussian surface, on any point on that Gaussian surface, if d bar is normal, so we have to equate it to total charge enclosed by the surface, and if d bar is tangential, then that value will become 0. Now, so what will be the symmetry for this point charge q? So that means, so due to this point charge q placed at the origin, where we can find d bar, if you join all such points where we can find d bar, then the closed surface of all such points will give you the Gaussian surface. Now, the point charge was placed at the origin. Then what are the various possibilities to find d bar surrounding this? You can find the d bar in this direction, in this direction, in this direction, and in this direction also. So for example, here I have taken only 4 directions. So like that, you can take all possible directions, right side, left side, top side, bottom side, out of the screen and into the screen also. Then if you join all such points, so what we will get is a sphere like this. We will get a sphere. Now this sphere is the Gaussian surface for a point charge placed at the origin. Now, so what we have to do is, on any point on this Gaussian surface, we have to apply the Gauss law to find out the electric flux density. So then, applying Gauss law at a point P, which is having some distance rho or r from this origin, then at this point P, to find out d bar, we have to apply the Gauss law. So how to apply Gauss law? So that is nothing but closed integral over S d bar dot ds bar should be equals to the total charge enclosed, that is q. So that is q should be equals to, so what here? So we are finding the d bar at point P. So that we can consider as d rho into what is remaining, closed integral over S ds bar. Now this can be written as d rho into, so this closed integral over S ds bar. So here if we are applying Gauss law, no need to evaluate this closed integral over S ds bar. It is same as the surface area of the sphere, which is the Gaussian surface. So what is the surface area of the sphere? It is 4 pi r square. If it is r is the radius. Here in place of r, what we are having? Rho. So therefore 4 pi rho square is the surface area of the sphere. Then from this we can write d rho equals to q by 4 pi rho square, or in general we can write in any direction d bar equals to q by 4 pi rho square into a rho bar, which is the vector associated in the direction of rho. So then with single step, so just by knowing the surface area of the sphere, now we got directly d bar as q by 4 pi rho square into a rho bar. But whereas in Coulomb's law, we have evaluated this closed integral over S by taking pi from the limits 0 to 2 pi and rho is from 0 to some infinity. We have evaluated the integral. So that complexity was totally avoided, totally eliminated here. So just by knowing the surface area of the Gaussian surface we got. So the here closed integral over S ds bar is nothing but the surface area, that is 4 pi r square of the sphere. So with this single step, single point, that is knowing the Gaussian surface area, we got the answer within a single step very easily. Yes or no? But the same d bar, by using Coulomb's law, we have to evaluate the integral. Here no need to evaluate the integral, only what we want is we have to identify the Gaussian surface. Once you identified the Gaussian surface, then the problem was almost solved. Just by equating it to total charge enclosed, we will get easily the total charge as well as the total electric flux density due to that given charge distribution. Now we will see the second application of Gauss law, that is infinite line charge, which was a very big problem we have already solved by using Coulomb's law. Now, so in order to apply the Gauss law for infinite line charge, now again consider a well-known Cartesian coordinate system consisting of x, y and z as shown. Then let us assume that an infinite line charge was placed along the z-axis, as we have considered the same problem in the case of Gauss law also. In the same way we are considering the line charge was existing on the z-axis. Now, what we want in order to get the d bar due to this infinite line charge placed on the z-axis by applying Gauss law is we want a closed surface called Gaussian surface. So, what is the Gaussian surface if the line charge was placed along the z-axis? So, how to get the Gaussian surface? So, surrounding this infinite line charge, what are the points? At what point we can find the d bar? So, if you join all such points, so that closed surface is nothing but the Gaussian surface, right? So, what are those points? So, where we can find the d bar? So, from this infinite line charge placed on the z-axis, right? So, we can find in the right direction of this infinite line charge, left direction, out of the screen, into the screen, and top side and bottom side, right? If you join all such points, so then what is the final shape we will get is a cylinder, right? So now by assuming an infinite line charge which is having a uniform line charge density rho L dl bar, then surrounding this you may have a cylinder which is formed like this. So this cylinder is our Gaussian surface, right? So now, so how will be the d bar on any point on this Gaussian surface? That is the second condition we have to apply. Now coming to that point, now so towards the right direction, so the electric field or electric flux density will exist in this direction, and left side, so it will be like this, right? Then top side it will be like this. So how we are drawing these all arrows? Because already we know d bar is always in the normal direction, right? So normal direction of what? That is infinite line charge, right? Similarly, for the bottom face of the cylinder, we will have the d bar like this. So that means, so if you identify all these arrows, at what points you can find d bar? So towards the right direction, you will have the electric flux density as normal to the line charge, whereas if you observe top and bottom, they are in the same direction of the infinite line charge. So that means for the top and bottom faces of this cylinder, you may get the d bar tangential, and whereas for the rectangular portion of the cylinder, we will have the normal component. So this is having a rectangular component of length L, then towards this length L, for the entire length of L, the d bar will be in the normal position, whereas for top surfaces of the cylinder it will be tangential. So once if it is tangential, then there will be no field exists. Then so in this direction you may have, suppose if you consider a point P on the one point of the cylinder, then let us consider that point as P, and it is having a distance of rho from the infinite line charge. Then at this point P, we have to find out the d bar by applying the Gauss law. So before that, how will be this d bar? It is normal for the entire rectangular portion of the cylinder, and it will be tangential for the top and bottom faces of the cylinder, like this. And left side also it is having the same distance rho, and it will be normal, but whereas coming to top, it will be tangential. So that's why here I represented it as dt bar. So this dt bar. So this dt bar will be 0 for the top and as well as the bottom. So finally, from the figure, what we can write is, for the cylindrical Gaussian surface, the electric flux density will be normal to the rectangular face of the cylinder along its length L, and it is tangential to the top and bottom surfaces of the cylinder. So that means we have to apply the Gauss law only for the rectangular portion of the cylinder to get the d bar for this infinite line charge placed along the, it is here. So one more point we have to assume is, so even though it was infinite line charge, to construct the Gaussian surface we have considered only a finite line charge. And here our assumption is the top point of the line charge is at infinity and the bottom point of the line charge is at the minus infinity. But in order to understand clearly, so we have taken a finite line charge only. Once we identified the Gaussian surface for the given charge distribution, the problem was almost over. Now what is the remaining is, so we have to apply the Gauss law for the portions where d bar is normal. So here the d bar is normal in which directions? Along the rectangular portion of the cylinder only. For the top and bottom surfaces it is 0. Now we are applying the Gauss law for the rectangular portion. By applying Gauss law, what is Gauss law? Closed integral over S d bar dot ds bar should be equals to q enclosed. So what is the q enclosed for this infinite line charge placed along z axis? So it is rho L into along length of the cylinder. How much is the length we have considered? L. So rho L into L becomes the total charge enclosed. Rho L into L. So that should be equals to what? So if you want to find out the d bar at a particular point P, then it is having a perpendicular distance of rho, then the d bar can be evaluated as d rho into a rho bar. Now, so d rho is the electric flux density at a point P having a distance of rho. Now, what is remaining? So, I have to integrate all such points throughout the surface ds. So, that is closed integral over S ds bar. Now, the same point here, we can write it as d rho into, so what is closed integral over S ds bar? Don't evaluate the integral because we are applying Gauss law here. So without evaluating the integral, so what should be the value? So that is nothing but the surface area of the cylinder. So what is the surface area of the cylinder having a length of L and a radius as rho? Here rho will become the radius of the cylinder also. Then, so what is the surface area of the cylinder with the radius rho and height or length L? So what is that? It is 2 pi rho L. Yes or no? Then from this what we can write to d rho? D rho equals to q enclosed, that is rho L into L divided by 2 pi rho L. Or in general, in any direction, d bar is equals to, so here LL gets cancelled. So in the numerator you will have rho L divided by, in the denominator also L gets cancelled, then 2 pi rho into, so what is the vector? A rho bar. Here rho is the perpendicular distance from the line charge to the point P where you are finding the d bar field. So here also with a single step we got d bar as rho L by 2 pi rho A rho bar. The same answer we got in by applying Coulomb's law also, but there we have evaluated this integral. So that evaluation of integral is a complex task. Now that complex task was totally eliminated here in the application of Gauss law. Then here also, what is the crucial point? So this closed integral over S ds bar is same as the surface area of the cylinder, that is 2 pi rho L. So these two will be equals to the surface area of the Gaussian surface, which is a cylinder. So like this, if you identify the Gaussian surface which is a closed surface, then the problem is very simple by using Gauss law, right? Students, after seeing the first two applications of Gauss law, that is for point charge and infinite line charge, can you tell me, by applying Gauss law, the solving of electrostatic problems becomes easy? I think you know the answer very well. Your answer is, I think it is Gauss law, right? So out of all the 5 applications of Gauss law, in this video we have seen for point charge and infinite line charge, and the remaining 3, infinite surface charge, infinite volume charge and uniformly charged sphere, how to apply Gauss law for these 3. So that we will see in the next video. I hope you have enjoyed our today's lecture on applications of Gauss law. So if you really like this video, please share to your friends also, and thanks for watching. See you in the next video. Thank you. Bye bye.